Hi everybody, welcome back, and today we'll go deeper into the atomic structure. So the model of atom has a long history, starting from Dalton model, okay, which see the atom as a small particle without anything inside it. Then Thomson suggests that the atom has small particles, small of positive and negative charged particles inside it. Then Rutherford model explained the atom as a center which is surrounded with negative charge particles. Then Bohr's model is usually used in our books. This is the standard explanation of the atom. And Bohr suggested that the atom is formed of a nucleus. The nucleus has positive protons and negative neutrons. And the total charge of the nucleus is positive, and it is surrounded by electron shells, which contain electrons, and these electrons are negatively charged. Schrödinger has explained the cloud model, the charge cloud model. So Schrödinger has some edits on the Bohr's model. He said that the electrons are not moving around the nucleus in a specific path, but it moves in an area called the electron cloud. Okay, electrons are moving around the nucleus in their electron shell. So in any neutral atom, the number of protons, which are positive, equal to the number of negative electrons. And we have explained that before. The mass number is the number of protons and the number of neutrons. And there is a symbol this is the symbol of the atom. You can see in the periodic table of the element. And the atomic number is the number of protons, which equals to the number of electrons. Just to recap what we have did before. Okay, so electrons exist around the nucleus in something called the energy shell. Starting from inside to outside, the shells have more energy. They have higher energy levels. And for electrons to be distributed, they start with the lowest energy levels to the highest one. That's why when we configure electrons, we start with the innermost shell, then the outer until the outermost shell. The innermost shell has the lowest energy, and the outermost shell has the highest energy. So usual explanation, illustration of the energy shell is like rings where around the nucleus where the electrons move around. This is just to simplify the drawing. And the energy level is considered as full if it has 8 electrons, and this is the octet rule, except the first level, which is full with 2 electrons. The outermost shell is called the valence shell because it decides the valency of the atom, which means if the outer shell has 1 electron, so this atom is univalent, has only one its valency is 1. So it can lose this electron and form positive 1 ion. If the outermost shell has 7 electrons, it can accept one electron, so it's univalent too because it will turn to a negative one ion. So the valence electrons are the electrons that exist in the outermost shell, and they predict how the element will chemically react and what type of ions will be formed. Also, the outermost shell predicts the physical and the chemical properties of the element. So this element can be metal, non-metal. The decision comes from the outermost shell. So the outermost shell is very, very important, which is the valence shell and contains the valence electrons. This is the sodium atom. The sodium atom has 11 electrons distributed as, this is the magnesium atom. The magnesium atom has 12 electrons distributed as 2, 8, and 2. So the outermost shell has 2 electrons. The valence shell is 2. The valency is 2. So this magnesium atom, when it enter a chemical reaction, it will tend to lose these 2 electrons, forming a cation or a positive ion. We can use also Lewis dot diagram to show how the atoms will react, and to be easy to see whether this atom will gain or lose electrons. So the Lewis dot diagram will show the valence electrons of the element. And they are, this is useful to see how this valence electron will behave, whether they will need to gain or lose electrons to form a molecule. So how to draw the Lewis dot diagram? So usually we draw the symbol of the atom in the middle, okay? And we start distributing the electrons around it in 4 directions, but we don't pair any electron until the 4 directions are filled. So we'll add 1, then 2, 3, 4. If we still have electrons, we will start to pair. So we'll add the 5th electron here, 6, and so on. And we represent them electrons as dots. For example, if we take magnesium as an example. So we write the symbol of the magnesium, sorry. Okay, and then magnesium is 12, so 2, 8, 2. So the valence electrons are 2. So we'll distribute these 2 electrons. You will add 1 here, then 1 here. We don't pair them. So I can easily predict that this magnesium can lose these 2 electrons. Okay, for hydrogen, for example, hydrogen has only 1 electron. So we can add this electron here or here or here or here, anywhere. Okay. Chlorine, for example, chlorine is 17. So the electron configuration will be 287. So 7 will be in the outermost or the valence electron and will be drawn in the dot diagram, in the Lewis dot diagram. So we will start by adding electron in each position. So they are 4, we still have 3. So we'll start to pair them. As we can see here, chlorine will tend to accept an electron from another atom to pair this lone electron. So chlorine from the valency and from the Lewis dot diagram, now we know that chlorine will tend to accept and will tend to form negative charge. And we can see too that magnesium is tend to lose these two electrons, and it tends to form cation or positive electron. So Lewis dot is very useful in that. So this is chlorine, as I mentioned. Oxygen. Oxygen can accept two electrons to pair each one of the lone of the single electron of the two single electrons. So oxygen is divalent, so it can be turned into -2 electron. Potassium. So potassium 19, 2, 8, 8, and 1. So it has one electron at the outermost shell, and it tends to form a cation, a positive cation. This is your turn, so I will ask you to make the electron configuration to each of these atoms and to expect and predict whether these atoms will form positive or negative ions. Okay. Using both the electron configuration using the Bohr model, draw the nucleus in the middle and the electron shell, and the Lewis dot model. So these are examples, and here I will expect you to draw them. This is your homework. Okay, based on this example. In general, the idea of forming ions is that every atom needs to reach to the nearest noble gas, which is called the octet rule. The octet rule, which means that the outermost shell needs to be full of 8 electrons, except the first shell needs to be full with only 2 electrons. This makes the atoms more stable. So this is the periodic table. Okay. And these atoms, these elements are metal. They tend to reach to their nearest noble gases. And to do that, they will tend to lose electrons. Like lithium is 3, 2, 1. So to reach to helium, it will need to lose 1. Beryllium is 4. To reach to helium, the nearest noble gas will need to lose 2 electrons, and so on. So this red arrows displays the nearest noble gas for each group of elements, for each elements. The other side showing how the non-metals behave. The non-metal on the left of the periodic table will tend to reach to the octet state. So to be similar to the nearest noble gas. So if we look from nitrogen, oxygen, fluorine, they will tend to accept more electrons in the outermost shell to be full to reach the electron configuration of neon, which is 2 and 8. Neon is 10, 2 and 8. So a nitrogen, for example, will need 3 electrons, oxygen will need 2, fluorine will need 1, and so on. So the basic idea is that being stable by having a full outer shell, by gaining or losing electrons from the outermost shell. If they are metal, they will tend to gain. If they are non-metal, they will tend to lose. And this will form charged atoms, or what is called the ions. So what are ions? Ions, they are charged atoms. But if this atom gains electrons, it will become negative ions or anions. Okay. And in that case, the equality between the number of protons and the number of electrons will be interrupted, which means if the atoms gain more electrons, so the number of electrons of that charged atom will be more than the number of protons. So the number of total negative charge will be more than the total number of positive charge in the same atom. So this will be anion or negative ion. This criteria is for the nonmetals because nonmetals have more than 4 electrons at the outer shell. They tend to gain. So nonmetals usually tend to gain electrons and form anions or negative ions. On the opposite, if the atom lose electrons, okay, so the number of electrons will become less than the number of protons. So the total positive charge will be more than the total negative charge. And in that case, the charged atom will be cation or positive ion. And this criteria, this property is specific for metals. Metals usually tend to lose electrons, their valence electrons, because they have less than 4 electrons at the valence shell. These are several ions, example of ions like chlorine gain 1 electron and it turned it into chloride ion, Cl negative 1. The charge refers to which type of ion and the number besides that charge tend to how many electrons were lost or gained. Because chlorine accepts 1 electron, it's negative 1. Sodium has only 1 electron in the valence shell. It tended to lose it out. So it has positive charge because it lost a negative charge, 1 negative charge, and it is positive 1. So another idea which is isotopes. Isotopes are atoms of the same element which have the same atomic number. Okay. But they have different neutrons. Again, let's remind you, the atomic number is the number of protons, which equals the number of electrons. Okay? But the atomic mass is the number of proton added to the number of neutrons, which is the number of the particles inside the nucleus, the mass of the nucleus. Okay, so isotope has the same number, the same atomic number. Okay, which means it's the same atom, forms of the same atom, but they have same protons and same neutrons and same electrons. But the different will be the number of neutrons. So they will have different atomic mass. Okay. Usually protons and electrons determine the chemical behavior. So isotopes, since they have the same atomic number, they will have the same chemical properties. But as the physical properties of an atom is determined by the mass, so isotopes have different physical properties. So isotopes of the same atom have similar chemical properties because they have the same number of protons and the same number of electrons, but they are different in the number of neutrons. So the total mass number of the nucleus will be different, and this will decide the physical properties of the atom. So isotopes of the same atom have different physical properties. Example of isotopes is hydrogen. Hydrogen exists in nature in 3 isotopes. Hydrogen 1, the normal hydrogen, which has 1 proton and 1 electron and has 0 neutrons. Deuteron, which isotope of hydrogen with 1 neutron, so the mass number is 2. And the tritium is another isotope of hydrogen with 3, the mass number of 3, which has 2 neutrons. So these are 3 isotopes of hydrogen that exist in nature. Each one of them has different physical properties, but chemically they behave like each other. So what is isotope abundance? Isotope abundance is what is the percentage of each isotope of atom exists in nature. As I mentioned, that hydrogen has 3 isotopes. So what is the percentage of each isotope of nature? So it is the percentage of a given isotope in the sample of an element. When we take a sample of an element, what is the percentage of each isotope of this element? And the atoms that exist in nature as isotopes, for them we calculate the average atomic mass number. That's why when we look at the periodic table, we can see strange atomic masses, like the chlorine atomic mass is 35.5. It doesn't mean that it has 0.5 neutrons, but it is the average atomic mass of the isotopes of chlorine. It is called AAM, or the average atomic mass. This mass and the abundance of isotopes are measured by mass spectrometer. So the unit of the average atomic mass is AMU, atomic mass unit, or U, or sometimes mu. Okay? And 1 atomic mass unit is estimated as 1/12 of the mass of carbon atom. We take the carbon 12 as a standard to measure them. Okay? If we measure it in grams, so 1 atomic mass unit equal to 1.7 times 10 to the power 20 minus 24 grams, which equals to 1.5 times 10 to the power negative 27 kilograms. 1 unit is the mass of 1 proton or 1 neutron. So every proton and every neutron has a mass of 1 unit. So to calculate the average atomic mass, or the AAM, if we have an element with 3 isotopes A, B, C, okay, to calculate its average atomic mass, we will multiply the percentage of the first isotope by its mass and divide it by 100. And then the percentage of the second isotope will be multiplied by its mass and divided by 100. And the percentage of the third isotope multiplied by its mass and divided by 100, and we add these together. We sum all of these together, we will get the average atomic mass of this element. Let's take an example, okay? This lithium. Lithium has 2 isotopes. The 6, one with the atomic mass of 6, which exists in this percentage, 7.42, and another isotope with atomic mass of 7 and the percentage of 92.58. How to calculate the average atomic mass of lithium? We have to follow the above rule, okay? Which is the percentage of isotope 1, which is 7.42, okay? Times its mass, which is 6, divided by 100, because it is 7.42 percentage. And we will add to it the other isotope as its percentage multiplied by its mass, which is 7, divided by 100. And then when we calculate this, we will get the average atomic mass of lithium. Okay, let's see. So the answer we will get after calculating the average atomic mass, we will get this number, unit or mu, and we usually round it to the nearest two decimals. So it will be 6.93 units. Other isotopes such as magnesium 24, this number is the mass. Okay. And magnesium 25 and magnesium 26. And their abundance, their percentage. The middle column represents the symbol of the atom with the atomic number and the atomic mass. So we'll consider only the atomic mass and the percentage. How to calculate the average atomic mass of magnesium? The same as we did before, average atomic mass of magnesium. We have 3 isotopes, so we'll multiply every mass with its percentage divided by 1 and sum all of them together. So the first percentage is that 78.6 times the mass, which is 24, divided by 100. Add it to the second percentage, which is 10.1, multiplied by the second mass, second isotope mass, divided by 100, and plus the third isotope percentage, multiplied by its mass, which is 26, divided by 100. Calculate all of these and give the final average atomic mass, and the value is, the unit is U or mu. Okay, try it yourself. I will give you some example, some problems to solve them yourself. So this is to calculate the atomic mass of copper. There are 2 isotopes. This is the mass, and this is the percentage. Okay, calculate it and write down the calculation in the comments down below. Chlorine, the same way, mass and abundance or percentage. And the iron, try to take a screenshot or to pause the video and solve it. It's very important to solve it. Okay. So other example of isotopes are oxygen. Oxygen has 3 isotopes, one of atomic mass of 16 and 17 and 18. Carbon has 3 isotopes, 12, 14, and 16. So the ratio of neutrons to protons. As we can see, as the protons increases in isotopes, the neutrons increases much more in the isotopes. These are our other example of isotope. The periodic table, as you can see, I think now you can recognize what I meant before by strange atomic masses. As you can see, cobalt, iron. So all of these strange masses means that there is average mass number calculated by all the isotopes of this element.